Welcome back to Chibuzor Mathphysics. Hope you have been doing great. And in today's video, we are looking at complex analysis. Complex analysis is all about complex numbers, and then you might need to refer to the introduction on complex analysis. So you can watch my previous video on when I took time to talk about what actually is complex analysis. So in today's video, it is all about complex analysis, and we will be looking at limits. We'll be looking at uniqueness of limits. We're also going to consider continuity, and then we'll talk about some properties and derivatives, and that will be the end of today's video. Of course, if time permits, we can look at some analytical functions in terms of complex analysis. So let us get started. When we talk about complex analysis in terms of the limit, what actually are we talking about? So let us start with limit in terms of complex analysis. We usually say that we can let some function to be defined at a point. If we let that function to be defined at a point, for instance, let us let f, for instance, we can let f to be a function. And this function is defined at a point. We define these at a point. And this up point, we can call it z or z, and this z is what we call neighborhood. We can say that z in some neighborhood. Z in some neighborhood. If you study reanalysis, you will know what we mean by neighborhood. And this neighborhood, we can call it z naught. So let it be z naught, except possibly for the point z naught itself. So it is except possibly for the point z naught itself. So what we are actually saying here is that the limit of f of z, the limit of f of z in this case, as z tends or approaches z naught, as this z approaches z naught, is a number. And in this case, we can call it W naught. We can call it W naught. So in a real sense, we can write this mathematically to be equivalent to the limit. For instance, the limit as z turned to z naught of this function f of z will be equal to W naught. So this is exactly what complex analysis tend to explain the secret behind this limit and its continuity. It also helps us to study the uniqueness of any limit that we talk about. When you talk about a uniqueness of a limit, when limit of a function, in this case we are talking about function that is indicated in the form of f of z. So if this function exists at a point, if it exists at a point, and in this case the point is z0, now it must be unique. It must be unique. It must be unique. If it exists at a point, z0, because we say that the limit, this is limit, we are talking about the limit as this function f of z, as z tend to z0 of this function f of z will be equals to w0. What we are referring to is that the f of z, this function exists. When the limit of a function exists at a point z0, then it must be unique. And now what we do in complex analysis is that you need to prove that what we actually say here is true or false. So we have to prove that the limit of a function f of z exists at a point z0, and it must be unique. So this is what we do in complex analysis, which I say that it is also good if you have background knowledge of reanalysis, because in reanalysis we also prove theorems that help us understand that a function is actually true or false, and that takes us to another laws that we call the laws of contradiction. So here we need to prove that this function, the limit of a function f of z, exists at a point z0, and if it exists at this point z0, it means that it must be unique. It must be unique. It must be unique. So now let us prove this. We want to prove that this function is unique. We want to prove that, so let us get rid of this. Okay, now let's suppose that the function f of z has two different limits. So to prove that this is unique, we want to prove. So we start by saying, suppose the function is f of z. Suppose this f of z has two different limits. Let's say it has two different limits. Two different limits. And let's call the first limit w0. And let's call the second limit w1. This is w0, and then we have w1. w1. So if then for a positive number epsilon, so we say that for a positive number epsilon, let's continue from here. For a positive number epsilon, this is a symbol for epsilon. Then there are positive numbers. This, for a positive number epsilon, what it means is that there are positive numbers. And these numbers we can call it delta naught and delta 1. This can be 1. such that if we try to represent this, what this simply means is that f of z in this case minus the first limit. In this case, our first limit is w naught. It is w naught. This must be less than epsilon. This must be less than epsilon. It must be less than epsilon, because we know here for a positive number epsilon, if there is a two different limit w0 and w1 for a positive number epsilon, so f of z minus the first limit must be less than epsilon. So what this means is that whenever whenever 0 is less than z minus z naught, that is fz minus z naught, then it is also less than delta naught. And for the second one, we have f of z minus the second limit w1. This also tells us that it is less than epsilon whenever 0 is less than z minus z naught. This is z minus z naught, and this will be less than delta 1. This will be less than delta 1. So the limit, we can let delta to be equals to some minutes in terms of delta naught and delta 1. Then for every 0 which is less than z minus z naught, it is also less than delta naught. It is also less than delta naught. What this means in a real sense, let me take a different color. What this means in a real sense is that f of z minus w naught, let's minus this, minus f of z minus w1, that is the second limit. This is the second limit. This must be less than equal to the f of z in this case minus w naught plus f of z minus w1, and this must be less than 2 epsilon, because we know we have 1 epsilon in the first one, in the first limit, and we have another epsilon in the second limit. So that is, it is less than this 2 epsilon. In that case, we simply mean that w1 minus w, this is w naught, w1 minus w naught is less than 2 epsilon. This is less than 2 epsilon. But we know that w naught, or let's say w1 minus w naught, is a constant, and we know this is a constant, and we know also that epsilon, in this case, epsilon can be chosen as arbitrarily a very small number. It is arbitrarily small. So if we choose epsilon, since epsilon is an arbitrarily small, so we can choose epsilon to be equals to 0. So if w1 minus w naught is equal to 0, then the limit of this function is unique, because we know if we choose that function, it will simply be 0. So that's why we say that it is unique. So this is hereby